What if the force and displacement are not aligned? Only the component of the force along the displacement does work. A force perpendicular to the actual displacement does no work because it does not change the energy state of the system. We express that by modifying our definition to allow the force to act at an angle theta to the displacement. In that case, we have a new formula or an extended formula where the work is now defined as Fd times the cosine of the angle between the force and the displacement. We're doing that because what we're really saying is that if the thing moves this way, but the force is this way with some angle between them, that force could be thought of being some part up and some part aligned. And when this is perpendicular, we get 0 work. But this part is only F cos theta. And stringing all that together, we get Fd cos theta. You could think of this, and it would not be crazy, as F cosine theta times d. But that's awkward to keep writing with the parentheses, so we usually write as Fd cos theta. Note that in this formulation, F is the magnitude of the force and d is the magnitude of the displacement, so they are each strictly positive, or I guess at worst case, 0. That means the sign of the work would depend only on the angle theta. There are basically 4 or maybe 5 easy cases. We might have them completely aligned, as we do in this top circumstance. In that case, the angle is 0, so the cosine of the angle is 1, and the work is just our naive case, F times d. So we recovered the one we had before. We could have an acute angle. Angle theta is more than 0 but less than 90. In that case, cosine of theta is going to be more than 0 but less than 1, and we get Fd cos theta exactly as expected, some positive number. We could have a perpendicular force, like, say, a rope trying to lift a thing which something else is pushing over. In that case, the angle is 90 because the angle is a right angle. And the cosine of 90 is 0, so the work done is 0. Or we could have a thing where, for instance, someone pushes a box really hard this way and then pulls back on it with a force on this rope, in which case the angle is obtuse, more than 90. Since the acute angle is more than 90, the cosine is negative. All right, the work is a negative number because it's positive number times negative number. And then the last case would be, what if the thing was being pulled directly backward? And in that case, the angle between them is 180, and the cosine of 180 is minus 1, so the work is negative. In fact, in this case, the work would be not Fd, but minus Fd, the least that it could be. So, a constant force F pushes a particle through a displacement delta r. Fine. In which of these cases does the force do negative work? Where here we have the force is pointing rightward and delta r points that way. Or the force is pointing leftward and delta r is that way. Or the force points leftward and delta r is also leftward. We also allow the possibility that is negative in A and C. Or sorry, negative A and B, or negative in A and C. The key thing isn't the rightward or leftward or wherever your things are pointing, but only their relative angle. And we see in this case that we have an obtuse angle here and an obtuse angle here. And in both cases, that gives us the negative because the force is sort of opposed. Or you could imagine projecting F into this part and the right angle that part, these two components, and this component doesn't do anything, right? Because we can also draw it as being up here where it is perpendicular, but this component is directly opposed, and so therefore we know it does negative work. And something similar happens here. On the other hand, in C, they are both aligned. In fact, they're perfectly aligned, and so C would have our definition of positive work. Our answer here is D. Which force does the most work? All three displacements here are given as the same. And we look at these things are first, well, our first instinct or first thing should be, wait, this is at right angles, so we know there's 0 work done in that case, so that is certainly not the answer. Which means, of course, this is also can't be the answer. In case, in B and C, they both do positive work. Right? They're both pointing more in the force is along or more along than against R. But if we look at that, the part of F that matters in this case is this part, and that's only 4 newtons long because it's going to be 8 newtons over the thing I'm looking for is going to be the cosine of the 60 degrees. So Fx is going to be 8 newtons times cosine of 60, which is a half, or 4 newtons. And so the effective force is much less, so it ends up being that it must be the 6 Newton force that is does the greatest work. All right, let's turn around. If we could vary the angle, find the angle at which the 8 Newton force would do as much work as the 6 Newton force, assuming that the displacements are the same still. So remember, we're going to have here's our displacements. In one case, we had the 6 newtons this way. And what I need to have is that when I project this thing of 8 newtons through some angle theta, I need that to yield 6 newtons. So 8 newtons times the cosine of theta is 6 newtons. The cosine of theta is 6 newtons over 8 newtons. Theta is the inverse cosine of 6/8, which you throw into a calculator and it tells you it's 41 degrees. All right, a strap inclined upward at a 45-degree angle pulls a suitcase through the airport. The tension in the strap is 20 newtons. How many joules of work does the tension do if the suitcase is pulled 100 meters at a constant speed? So we go through and we say, well, our work is going to be the force times the displacement times the cosine of the angle between them. The force is 20 newtons. It's the tension in the strap. The distance, they said, was 100 meters. And then cosine of 45 degrees. This turns out to be 14 newtons, which I guess, given really only one sig fig, or merely at best 2, something like 1400 newtons. Okay, what can be said about the sign of the work done by the drag force of the parachute slows the drag racer down? Is it positive, 0, negative, or depends on which way the racer is moving? And here it's going to be negative. The drag racer moves some direction, and the drag of the force on the parachute has to point the other way, which means the angle between them is 180, so we get negative work.